Okay, we are continuing with graphing rationals. We're using the same handout that we used on Friday. On Friday, we did 1, 3, 4, 5, and 6. Okay, today we're going to do 7, 8, 9, 10, and 11. This type down here, the 12 and 13, we're going to talk about those in the next unit we cover. We're not going to worry about them just yet. And then 2 is really a very uninteresting example. That's why we skipped it. We're not going to worry about that. All right, so picking up with number 7, we want to get the top of that fraction factored. Plus 5. No, that's not right. What was I thinking? Just join. It's minus 5 plus 1. All right, some of the stuff we identify, it's nicer to look at this. And some of the stuff we identify, it's nicer to look at this. So my preference is look at it, spread it both ways to start the problem off with. Okay, our domain is all real numbers except for when the bottom of the fraction is equal to 0. So we have one restriction in the domain, x cannot equal positive 2. Now, as long as this is in simplified form, that restriction is going to manifest itself as a vertical asymptote. Okay, the next place that's my preference to go to is to get the intercepts. As long as this is in simplified form, the x-intercepts are going to be when the top of the fraction is equal to 0. So that's 0 at positive 5/2. That's 0 at negative 1. Positive 5/2 is 2.5. Right, for the y-intercept, it's nicer to look at the polynomial form. When you plug in 0 for x, all that stuff drops out. You're left with negative 5 over negative 2, which is positive 5/2. So 5/2 is a y-intercept, and it's an x-intercept. All right, for the horizontal asymptote, the degree of the top is bigger than the degree of the bottom. So this is the type that we did not address on Friday. If the degree of the top is bigger than the degree of the bottom, there is no horizontal asymptote. The cases that we did on Friday, they were either the same degree, in which case the horizontal asymptote would be at the ratio of the lead coefficients, or if the top is smaller than the bottom, then its y is equal to 0. This is the third possibility of what could occur. Now, if the top is exactly 1 bigger than the bottom, then it does have a slant asymptote. Okay, the way we actually find that slant asymptote is we're going to divide this out. We have 2 options to divide it out. We could use long division or synthetic division. A long division is kind of long. That's why they call it long division. We prefer not to use it if we don't have to. If we're dividing by a first-degree binomial with a lead coefficient of 1, we can use synthetic. Okay, first degree, meaning that exponent is 1. Binomial, 2 terms. Lead coefficient of 1. All the conditions get met to nicely and cleanly use synthetic division. So we take the opposite of that negative 2. That goes in our little division box. We list off our coefficients. Skip a space, draw a line. Do the synthetic division process. That comes straight down. That times this goes here. Add that column. That times this goes here. Add that column. If that is a degree 2, and we're dividing by a degree 1, and this is going to be a degree 1, it's always 1 less than what that was. Okay, our slant asymptote is going to be the part without the remainder. So that y equals 2x plus 1 is our slant asymptote. So we have a y-intercept of 1, a slope of 2. Looking like that. Right, all of these things that we've done so far, they're identifying the key features you should be doing without relying upon looking at a picture on a graphing calculator. Use a graphing calculator to flesh out the rest of the curve, and sometimes you need a graphing calculator to find your range. Okay, so it turns out that we have one branch that's doing this, and we have a second branch that's doing this. And each of those branches by themselves hit all the y values. Our range is all real numbers. Yes.
So for the you list all your coefficients.
Yeah, the 2, -3, -5.
I think you just drop the first one, multiply it.
Yeah, that comes straight down.
Yeah.
That times this goes here.
Yep.
Add the column. That times this goes there. Add the column. And then it's going to be 1 less than, if that's a degree 2, then this is a degree 1 in terms of how it starts. All right. Any other issues with number 7? Yes.
I just found out really being part of this problem, but in the remainder of the synthetic treatment, is it 3 over x minus 2 or x plus 2? I don't
X minus 2. It'll be whatever this was as is. Anything else? All right, next one, number 8. Sorry. The top factors into x, x minus 1. We have one restriction in the domain. X cannot equal -1. As long as this is in simplified form, that will manifest itself as a vertical asymptote. As long as this is in simplified form, your x-intercepts will be when the top of the fraction is equal to 0. At 0, at 1. If 0 is an x-intercept, then it has to be the y-intercept. All right, for the horizontal asymptote, the degree of the top is bigger than the degree of the bottom. Top is bigger than the bottom, there is no horizontal asymptote. If the top is bigger than the bottom by exactly 1, then we will have a slant asymptote. To find a slant asymptote, we need to divide this out. The preference would be to use synthetic division. Synthetic division is not always going to work. You may have to use long division, but synthetic works with this one as well. So we're taking the opposite of that +1 on the bottom here. When we list off our coefficients, we need 1, -1, and a 0 at the end. You always have to have descending order of exponents in one of every term. So if there's no constant term, we have to put a 0 there. Okay, that comes down. That times this goes here. Add that column. That times this goes there. Add that column. If that's a degree 2, this is a degree 1. The part without the remainder, that's your slant asymptote. So that has a y-intercept of -2, a slope of 1. And all of these things we've done so far, you should be calculating without relying upon your graphing calculator. Graphing calculator should be used for getting the rest of the curve fleshed out, and perhaps in this case, definitely identifying the range. So we end up getting one branch of the curve that looks like this, and the other one is like down here in this neighborhood like that. So for this problem, we need to identify that minimum point and we need to identify that maximum point in order to answer the range. In the interest of time, I already figured that out. This point here is at 0.41, negative 0.17. And that point there is at negative 2.41, negative 5.83. So using interval notation, smallest y to biggest y. We're going from negative infinity up to and including that y value. And then from that y value up. And unless you got some crazy math skills I'm not aware of, you can't do that without a calculator. Yes.
More of the points like that. Yeah.
Those 2 points right there, they were the x-intercepts, 0, 1. All right, now as far as what we needed to know to answer this question as is, we're done. But I want to talk about a couple things that are going to be important for what we're going to be doing in the next unit and also kind of help you connect some dots in your head. This original expression and this whole thing, including the remainder, are algebraically identical. They're the exact same thing written 2 different ways. Now, what happens is if you look at it in this form and you think about x getting infinitely large, when the bottom of this fraction gets really, really, really big, the entire fraction comes closer and closer and closer to 0, which means that this doesn't become very important for the overall shape of the graph. The overall shape of the graph, once you move away from that vertical asymptote, is going to look an awful lot like y is equal to x minus 2. That's why it approaches that asymptote like that. Now, the same thing happens in the negative direction. As you plug in negative 10, negative 100, negative 1,000, negative bazillion, this thing gets closer and closer and closer to 0, and the graph basically becomes y is equal to x minus 2, which is why that's happening down there in this direction. So although when you're in that close to the x is equal negative 1 neighborhood, that fraction's kind of a big deal. He thinks he's all that and the bag of chips. It turns out, though, once you get sufficiently away from that vertical asymptote, that's like a paper tiger, so to speak. It doesn't really have much impact on what's happening with the graph. Now, that idea about things happening at extreme values and involving infinity. We're going to be fleshing those out in our limits unit coming next. But this just helps you kind of make sense of why that graph looks the way it does, and kind of like sowing the seeds, so to speak, of what we're going to be talking about next. All right, good with number 8? All right, now on to number 9. We're getting a different set of instructions here because of the fact of these are going to play out a little bit differently than the ones above. So for 9, 10, and 11, it's asking us for the domain, the vertical asymptotes, and the removable discontinuities. All right, so this is our original function. When we factor the numerator, it gets us here. And then for the first time, something's actually canceling. Numbers 1 through 8, nothing ever canceled and ever reduced down to anything else. So how does that play out in terms of what we do, how we graph it, how we name it, how do we describe it, et cetera, et cetera? Okay, well, first of all, you're always identifying domain before anything reduces and cancels. In the final reduced form, there are no restrictions in a domain, but it's the original one that we're identifying. So our domain is we have a restriction x cannot equal 2. Now, if that x minus 2 is not present in the bottom or the simplified version, it's not going to be a vertical asymptote. This is going to be a removable discontinuity. A removable discontinuity is awkward to say and it's long to write. It's very often just referred to as a hole in the graph. We're going to have a hole in the graph at 2 comma something. Now, since there are no restrictions in the domain for the final reduced form, it means we are going to have no vertical asymptotes. So this original function we started with really isn't even in the same category with everything else we've talked about so far. This is just a linear function with a hole, is all it is. So when we graph this, we're going to graph the line y is equal to 2x plus 3, and we're going to show a hole at 2 comma whatever. So this has a y-intercept of 3, slope of 2. Oops, I didn't count right on that one. Slope of 2, up like that. So at x is equal to 2, that means we're going to have a hole right there. So the y coordinate of that hole is 1, 2, 3, 4, 5, 6, 7. So the hole, or the removable discontinuity, its more formal name, is at 2, 7. Now, we're not always going to have a graph in order to identify the y coordinate of the hole, or it may be a little too time-consuming to produce that graph. So the nice shortcut that always works is if you plug that 2 into the simplified version, that gives you the y coordinate of the hole. So plug the 2 in here. 2 times 2 is 4. 4 plus 3 is 7. You can get the 7 that way rather than looking at the graph. Good with that? All right, other thing of note here. One of the things I had said each time we identified x-intercepts in the first 8 problems, as long as this was in simplified form, the x-intercept was where the top of the fraction was equal to 0. So we have an x-intercept at -3/2, but we certainly don't have an x-intercept at 2. Okay, we don't have an x-intercept at 2 because we have a hole at 2. Okay, once you're a hole, you're nothing else. Perhaps you know some people in your life that you've classified as certain types of holes. They're nothing else in your world once they hit that classification. If you're a hole, you're nothing else. You cannot be a hole and an x-intercept at the same time. Politically incorrect as it may be, it happens to be something that usually students remember. All right, we good with that one? All right, on to number 10. I should do it down here since we really don't fit that category up there. And what do they want? Vertical asymptotes holes. Okay, so for number 10, we need to get the top of the fraction factored. It's got 4 terms. You have to do factor by grouping. Take an x squared out of the first half, -4 out of the second half. X plus 3's match. These guys make up the other binomial. And once again, we have something canceling out. The x plus 3's cancel. All right, so the domain. You're always going to figure out the domain before things reduce or cancel. So we have a restriction. X cannot equal -3. If that x plus 3 is still there in a simplified form, that means it's going to be a vertical asymptote. If that x plus 3 is canceling out in its simplified form, then it's going to be a hole instead of a vertical asymptote. Now, we could get the y-coordinate of the hole from the graph after we graph it, or what we could do is plug that -3 into the simplified version. So the hole we know is at -3, +5. If we don't have anything in the bottom of the fraction in the simplified form that's causing a restriction, it means there are no vertical asymptotes. So the best description of this graph, which has that same flavor as numbers 1 through 8, it really simplifies down to just a quadratic with a hole. It's x squared minus 4 with a hole at -3, 5. I can't spell quadratic. So we're going to graph the parabola x squared minus 4, and we're going to show a hole at -3, 5. Yes. Bottom. If I said the top, I misspoke. I apologize. Yeah, it's when the bottom of the fraction is equal to 0. All right, so this is your basic parabola bumped down 4 units. So you're bringing the vertex down to 0, -4. It's standard width, so we can use the shortcut over 1 up 1, over 1 up 3, over 1 up 1, 2, 3, 4, 5. Mirror image on the other side. And then we need to draw in a hole at -3, 5. Yes.
So from like that, it's technically called the origin, right? Or no, the vertex. From the
Yeah.
vertex, up 1 over 1, up 3 over 1, up 5 over 1.
Well, up 1, over 1, up 1, over 1, up 3, over 1, up 5. Yeah. And if you forget, you can always just plot a couple points. All right, going back to that your whole nothing else thing. If you look at when the top of the fraction is equal to 0, that x squared minus 4, that's still there when we simplify. We have x-intercepts at +2, -2. We do not have an x-intercept at -3, because at -3 we have a whole, and it can be nothing else. Good with 10? All right, one more for today. All right, so from our original function, we could factor a 6 out of the top. The bottom factors in x minus 4x plus 2. X plus 2's cancel, and that's 6 over x minus 4 is the simplified version. All right, domain, we're identifying before things reduce or cancel. So we have 2 restrictions in a domain. X cannot equal +4 or -2. Now that -4, or the x minus 4, which produces the restriction x is equal to 4, is still there in a simplified form. If that's still there in a simplified form, then we have a vertical asymptote at 4. The thing that's producing the restriction for the -2 is canceling out. So we have a hole at -2. So this one has a vertical asymptote and a hole in the same problem. If we want the y coordinate of the hole, we can plug into the simplified version. We get 6 over -6 or -1. So we have a vertical asymptote at 4. We have a hole at -2, -1. Now, in the simplified form, this still has the same basic flavor of the first 8 we did. So we can still address the other things that we talked about prior to today. So for example, x-intercept, when is the top of the fraction equal to 0? Well, it was there, but that canceled out. It's already a whole. 6 can never be 0, so we don't have an x-intercept. Okay, y-intercept, we can plug 0 into any form we want. It's going to give us the same answer. We plug it into the bottom. 6 over -4 is -3/2, -1.5. We have a y-intercept. The degree of the top is less than the degree of the bottom. It doesn't matter which one you look at. So we know we have a horizontal asymptote at y is equal to 0. So we end up getting one branch here, another one up here. The degree of the top is less than the degree of the bottom. All right, let's take a look at what we can see on a calculator and what we can't. All right, I have the original function already plugged into y1, and I have the simplified version plugged into y2. I'm going to turn off the simplified version for now. I don't want to see that. I just want to see the original version. Okay, if we hit graph, it certainly looks pretty good compared to what we drew by hand. Now, seeing that picture, it's pretty safe to assume that you got that vertical asymptote there at x is equal to 4. The feature that you're not seeing on the calculator is the calculator doesn't draw a little hole for you there. It appears as just being a normal continuous point on a graph. So this kind of plays to what I had said multiple times of there are certain things that you're not going to be able to tell from looking at a picture on a graphic calculator. Okay, just looking at that picture, there's no indication that you have a hole at -2, -1. Now, if you go to your table and you look, we have errors at -2 and 4. Just looking at the table, we don't know why that's an error. We just know there's an error at those two values. In combination with that table and that graph, you can piece it together that if it doesn't appear as though we have a vertical asymptote at that x is equal to -2, probably a pretty safe bet that it must be a hole instead of a vertical asymptote. There are a couple other things it could be that we're going to talk about in our next unit, but based on what we know right here, right now, it's got to be one of those two things. Well, clearly it's not a vertical asymptote, so it must be a hole. Yes. Well, vertical asymptotes have to be figured out in combination with the before and after. The horizontal asymptote, as long as it's still a rational and it didn't like simplify down to like a linear with a hole or a quadratic with a hole, then it doesn't matter which version you look at. It'll be the same either way.
Like in this case, though, it's
Well, the degree of the top is less than the degree of the bottom in either case, and it still fits that rational category. So no matter which you look at, y equals 0 is the horizontal asymptote.
Would there ever be where you simplify and that's not like
Not right now. We're going to look at different variations next unit, but as of right now, then it doesn't get any more like obscure than what we just did. All right, anything else with this one? All right, those of you at home, if you have any problems or questions, this would be the time to ask.